Throw a coffee mug against a tile floor. Watch it explode into a dozen jagged pieces. Now genuinely ask yourself, why can't it just snap back together? You'd probably laugh at the question. Obviously it can't. That's not how things work. But here's what nobody tells you. The physics that governs every atom in that mug, every collision, every vibration, every fragment flying through the air, that physics works just as perfectly in reverse. There is nothing, not one equation, not one law, that forbids those pieces from leaping off the floor and locking back into a perfect mug. So why don't they? That question, that seemingly ridiculous question, cracked open one of the deepest mysteries in all of science, and the man who did more than almost anyone to explain it wasn't a philosopher or a mystic. He was Richard Feynman, physicist, bongo player, safecracker, Nobel Prize winner, and he had a way of turning the most mind-bending ideas into something you could almost hold in your hands. What you're really asking when you ask about that mug is, why does time go forward? Why is yesterday fixed while tomorrow is open? Why do you carry memories in one direction and none in the other? The answer lives inside a concept called entropy. And once you truly understand it, the way Feynman understood it, you will never look at the ordinary world the same way again. Start with something simple. Imagine a brand new deck of playing cards, still sealed in the box, ordered by suit by number, perfectly sequenced from ace to king. That deck is in a very specific arrangement. There's essentially one way for a deck to look exactly like that. Now shuffle it. Shuffle it again and again. You will never in your lifetime accidentally shuffle that deck back into perfect factory order. Not because shuffling is incapable of producing that result. Technically it can. But because out of the billions upon billions of possible arrangements, only one of them is that pristine sequence. Every other arrangement is some version of chaos. So chaos wins, not by force, by sheer overwhelming probability. That's entropy, not disorder in the poetic sense. Entropy is a measurement of how many possible arrangements a system can have. A system with many possible arrangements has high entropy. A system locked into one very specific configuration has low entropy. And here's the rule that governs the universe at every scale. Systems don't flow toward low entropy, they flow toward high entropy. Always. Because high entropy states are simply more probable. Now apply that logic to your mug. An intact mug requires every molecule to sit in a precise relationship with every other molecule. Trillions of atoms all in their exact right place. There's essentially one way, one to be a mug, but a shattered mug? The fragments can scatter in countless configurations. Each shard can land at 1,000 different angles, 100 different positions. It doesn't matter which exact arrangement of broken pieces you get, it's still a broken mug. So when the mug falls, it's not obeying some mystical law that says objects must break. It's obeying probability. It's doing what's overwhelmingly more likely. And the chances of the reverse happening, every fragment simultaneously moving in exactly the right direction to reunite, are so astronomically small that you would need to wait trillions of times longer than the current age of the universe for it to happen by chance. This is the second law of thermodynamics. One of the most powerful statements in all of science. In any isolated system, entropy either increases or stays the same. It never spontaneously decreases. Pour cream into black coffee and watch it swirl and spread until the whole cup is uniform. You will never watch that cup spontaneously unmix itself, the cream pulling back into a swirling ribbon, separating cleanly from the coffee. That would require entropy to decrease. It doesn't happen. Feynman's great contribution to this conversation was insisting that the second law isn't a law in the way traffic laws are laws. Traffic laws exist because someone decided on them and enforces them. The second law exists because statistics are overwhelming. There's no enforcer. There's no prohibition. There's just probability pressing on reality so hard that the outcome looks inevitable because it practically is. Here's a thought experiment Feynman loved. Picture a glass box with a divider down the middle. On the left side, you pack in 1,000,000 air molecules. On the right side, nothing. A perfect vacuum. You remove the divider. What happens? The molecules rush into the empty space, and within microseconds they're spread throughout the whole box. Now wait, will they ever all crowd back to the left side on their own? The physics permits it. Each molecule is just bouncing around randomly, following perfectly reversible laws. But the probability of all 1 million molecules randomly ending up on one side simultaneously is so small that no number with a name is big enough to describe how unlikely it is. So it never happens. The expansion is irreversible, not because it's forbidden, but because the reverse is so improbable it's essentially fiction. Now here's the part that rewires your brain. The direction of time past to future, cause to effect, memory to anticipation. That direction isn't written into the fundamental equations of physics. Newton's laws, Maxwell's electromagnetism, Einstein's relativity, quantum mechanics, none of them distinguish between forward and backward in time. If you ran a film of two particles colliding and reversed it, a physicist examining the math couldn't tell you which version was real. Both versions satisfy the equations. Both are physically valid. So the arrow of time, the reason you feel like you're moving forward through history, the reason yesterday is solid and tomorrow is fog, that arrow is a consequence of entropy. It's not baked into space-time. It emerges from statistics. It emerges from the fact that when you're made of trillions of atoms interacting in complex ways, the overwhelming probability of entropy increase creates a one-way channel. The arrow isn't fundamental, it's emergent. And Feynman found that not disturbing but liberating, because it meant you could actually explain it. Think about how you identify before and after in any process. You watch a video clip of something burning. You instantly know which frame is earlier. The log is intact, the flame is growing, the ash hasn't accumulated yet. Entropy is lower. That's before. The log is ash, the heat has dispersed, the smoke has scattered. Entropy is higher. That's after. The arrow of time is just the arrow of entropy increase. They're the same thing, described differently. Now, memory. Why can you remember Tuesday but not next Tuesday? This feels like it has an obvious answer. Tuesday already happened, next Tuesday hasn't. But that's circular. From a physics standpoint, both the past and the future exist as states the universe occupies or will occupy. So why does your brain encode one and not the other? Feynman saw this clearly. Memory is a physical record. When you experience something, it changes the physical structure of your brain. Neurons strengthen their connections. Chemical states shift. A trace is carved into the material world. That trace is low entropy, a specific organized configuration that encodes information about what happened. But forming that trace costs energy. Your brain burns glucose. Heat dissipates into the air around you. Total entropy in the universe goes up even while local entropy in your neurons goes down. Memory formation is entropy's way of letting information leave a footprint while still balancing the cosmic books. And critically, that footprint is always a record of causes, never effects. Your brain's current state is the result of everything that has happened to you. The past pushed you to this moment. The future hasn't pushed anything yet, so there's no physical record of it. You can't remember what hasn't caused anything. But here's what's genuinely strange. In principle, if you could somehow reverse all the processes in the universe simultaneously, every particle, every collision, every vibration moving backward with perfect precision, your memories would run in reverse too. You would know the future and have no knowledge of the past. Your sense of before and after would flip, because memory, causation, and the arrow of time are all the same phenomenon. They all ride on entropy. This leads to the question Feynman took most seriously. Does the past still exist? In practical terms, no. You can't go back. The coffee has cooled, the mug has shattered, the moment is gone, but in physical terms, the answer is more complicated. When entropy increases, information gets scrambled, but it doesn't get destroyed. That's a bedrock principle of quantum mechanics. Information is conserved. So when your mug hit the floor, the information about its intact state didn't vanish. It redistributed. It's encoded in the precise positions and velocities of every shard, every sound wave that radiated outward, every tiny heat signature left on the tile. If you had perfect knowledge of the current state of every particle involved, you could theoretically run the equations backward and reconstruct the mug's history down to the nanosecond. The past isn't erased. It's hidden. It's scrambled across so many particles in such complex ways that no practical process can ever unscramble it, but the information exists. In principle, the past is present, ghost-like, encoded in the current arrangement of the world. Many physicists take this seriously in the context of what's called the block universe. In this view, all of space-time, every moment that has ever existed or ever will, exists simultaneously as a four-dimensional structure. Past, present, and future are not separate things. They're different coordinates. You experience now as special because you're embedded inside the structure, moving through it. But the moment you experienced an hour ago is still there, geometrically. It hasn't ceased to exist any more than Chicago ceases to exist when you drive away from it. But all of this leads back to a question Feynman was genuinely troubled by. Why did entropy start low in the first place? Every explanation for the arrow of time depends on the universe beginning in an extraordinarily low entropy state. Right after the Big Bang, matter and energy were distributed with remarkable smoothness. And when gravity is the dominant force, smooth means ordered. As gravity pulled matter into clumps, stars, galaxies, clusters, that was entropy increasing. The rich structure of the cosmos is the universe doing what all systems do, moving toward more probable arrangements. But why the smooth start? Why did the universe begin in such a special, improbable condition? Feynman didn't pretend to know. He'd say plainly that this is where our understanding runs out. Some physicists accept it as a boundary condition. Just how things started, no further explanation available. Others suspect that quantum gravity or inflation dynamics naturally select for low entropy initial conditions in ways we haven't fully worked out. Some invoke the anthropic principle. In a multiverse of possible universes, only those with low initial entropy develop the entropy gradients needed for stars, planets, chemistry, and life. We're here because we could only be here. It's a genuinely open question. And Feynman's response to open questions was always the same. Don't fill the gap with mysticism. Sit with the uncertainty. Keep working. Here's what makes all of this worth carrying with you. Every time something breaks, burns, cools, decays, or fades, you're watching the universe doing what it statistically must. The arrow of time isn't a cosmic rule handed down from above. It's the sound of probability settling over and over across trillions of particles in the direction of more ways to be. Memory, aging, causation, these are all the same story told from different angles. The story of a universe moving from unlikely to likely, from ordered to scattered, from one arrangement to many. The past is real. It's just inaccessible. It's encoded in the current state of everything, waiting to be read by a mind that doesn't exist and never will. The future is open. Not because the universe is free, but because entropy hasn't finished its work yet. And you, thinking about this right now, burning glucose to form a memory of these ideas, you are entropy in motion. You are the universe rearranging itself in the direction of more probable states. And somehow from that process, understanding emerges. That's not a small thing. That might be the most remarkable thing of all.